Good day, everyone. My name is Ali Tizradam. I am a principal technology architect at TELUS with focus on network softwareization. Today, I would like to share with you some thoughts on how telco service providers can move towards setting their network to a kind of autopilot mode. But before diving into details, who is TELUS? TELUS is among the largest telco service providers in Canada, operating nationally. It's a source of pride for us that TELUS has been constantly selected as the fastest mobile network in Canada, and recently, according to OpenSignal, as the fastest in the world. TELUS has been always a leader in sustainability, and it is the first Canadian company that is globally recognized as the world's most outstanding philanthropist company. To start the discussion, let's explain the playground first. Telco service providers are transitioning to a new era. The type of services are changing. Traditionally, in telco-based service providers, we have had services with long lifetime, such as voice, TV, and data. Nowadays, new services are required, which are more dynamic and typically with much shorter life cycle. One example is resource calendaring. We may also intend to optimize existing services. As an example, consider a video content provider with some local cache servers within service providers domain. Typically, content providers monitor the capacity of the network link connected to the cache and automatically downgrade the content quality if the link is highly utilized. This potentially affects telco service provider customers. With the emergence of new software-controlled optical switches, we have now the opportunity to instantiate wavelengths in optical layer using software and upgrade the capacity of the IP link connected to the cache to address this issue. Another challenge is the equipment price cost. The CapEx cost per port is significantly dropped, while the labor cost to install, configure, and provision the same port has remained almost constant. So we need to address the fact that OpEx or operational expenses are becoming a bigger and bigger component of our costs. To address all of these challenges, we need to build an ecosystem to enable converting high-level objectives or intents to a set of actionable policies and automatically execute them to quickly reshape the network, including its content or traffic. Moreover, the ecosystem has to offer an intelligent service and app development framework to enable rapid creation of innovative services and objectives, as well as automation and orchestration applications to optimize the OpEx cost. I guess it's obvious from the context that such ecosystem cannot be built without having a programmable network substrate, as well as capability of creating and instantiating complete negative feedback control loops. Network programmability is what enables a software sitting outside of a network to disseminate intelligence, but controlling the functionality of the network elements and the whole network state as a result. The network industry has gone a very long way in the last 15 years and made almost every part of network programmable, starting from customer premise equipment, where introduction of SD-WAN technology enabled inserting intelligence at the CPE level. Then segment routing enabled us to program the packet journey routes right at the edge of the network. In the optical domain, colorless, directionless, contentionless, and flex grid features enabled software control of optical core switches. Network function virtualization also made it possible for telco service providers to extend intelligence to the cloud and move many parts of traditional networking gear there. Having all of these programmable parts of the network provides the chance to build programmable service delivery platform at the top and enables us to create closed loop logics to realize different networking objectives intelligently. In TELUS, from a few years ago, we recognized the need for such ecosystem and started to build our own programmable service delivery platform that is called TINA. TINA stands for TELUS Intelligent Network Analytics and Automation Ecosystem. Here, I would like to double click a bit more on the concept of closed loop control. Let me start by reminding everyone that negative feedback control loop is not a new topic at all. it has been existing from 2000 years ago, and in 1920s it was fully formulated as we use it in all modern machines and factories today. The idea of negative feedback loop is that if we know what the optimum response of a system should look like, we always create an error signal showing the difference between desired output and the measured one. Then through the system, we try to feed the error as an input and apply a logic to minimize the error. In 2003, IBM introduced its blueprint for autonomic computing, where make loop or monitor, analyze, plan, execute cycle as control loop was introduced again, this time in the context of IT systems, with stress on having localized autonomic managers to create such loops to enable construction of a system that is capable of self-healing, self-configuring, self-optimizing, and self-managing. The key ingredients of IBM's system are shown in this picture. An autonomic manager monitors the sensor data, analyzes the raw data, and tries to understand the situation in the system or data center from the observed data, as well as the knowledge base that has been built over time. There is a plan module within the autonomic manager block that is taking the result of analysis and makes some decisions on how to evolve the system, and these results will be executed to the managed resource through effectors. There will be many such autonomic managers working to optimize different portions of the system, and there will be hierarchical managers to talk to the local ones. In today's world, these hierarchical managers are more defined as orchestrators. The term autonomic in the context of IBM's work is the ultimate level of system maturity that one can achieve, where we define our business desire, then the system will determine what needs to be done to fulfill the business request. In fact, from systems perspective, the journey has been to evolve from a basic reactive mode of operation to proactive, predictive, adaptive, and eventually autonomic, in which the components of the infrastructure are well integrated and dynamically manage themselves according to business rules and policies. Moreover, human body has been always a source of inspiration for control systems. When you get your hands close to fire, the first reaction of your body is to quickly push your hand back to stay away from fire and to protect you from more burning. Then if there is a burned area, there is a longer process that body starts to heal the skin. So there are two loops here. One fast loop that reacts quickly to the events to provide a short-term cue, and there is a slower loop that gets initiated afterward to try to re-optimize the state. From another angle, now that we all deal with COVID-19 pandemic more than before, we feel the need to improve defense system by inserting some sort of anomaly or mistakes to the mix. Nowadays, intent-based networking is the closest idea in networks to IBM's view of autonomic computing evolution. In the networks, we always have the current network state, which is collected and kept as single source of trust, while there is an intended state or single source of truth defined as intent that we would like to reach at. The intent-based networking paradigm is about making this movement from current state to the intended state automatically and intelligently. Self-driving networks leverages intent-based networking concepts and tries to build a set of automated, dynamically adjustable policies to steer and derive the network from source of trust towards the source of truth or intended state. The route to success in self-driving networks is similar to that of self-driving cars. In car industry, the movement towards self-driving cars started by first adding abundance of sensors to the car in order to enable collecting various data. In the next step, more and more software was introduced to convert the ingested sensor data to knowledge. Then little by little, isolated pieces of intelligence started to be included in the car. For example, we can name cruise control, parking assist, lane camera, and intelligent brake. Nowadays, we are witnessing that more and more intelligence is being added to the car control ecosystem that makes us closer to realizing the dream of having fully self-driving car. The journey of self-driving networks follow the same footprint. After the emergence of software-defined networking and introduction of programmable networks, as the first crawl step, idea of config as the code for automation started to flourish. Then we began walking to the model-driven domain of automation that in turn enables thinking about realizing policy-based automated control. And of course, the final step is to run into the race of using AI to convert a given intent to a set of policies to be executed in the network mix. Therefore, the key is to intelligently map a human-like intent to policy. Our vision is that there are 3 layers of policy types that are going to be in place. In first layer, we are using techniques like natural language processing to convert intent to formal high-level declarative language with a specific syntax understandable by machine. The second layer of policy type that we refer to as definitive will decompose a declarative policy to a set of actions for planning blocks in order to define decision-making activities. The lowest layer of policy types are imperative or prescriptive ones, which are pretty much the same as typical action policies. The main goal of self-driving networks is to intelligently build a tree of policies composed of all the policy types that we talked about, and to maintain an intent in its life cycle. So far, here and there, we have spoken about learning methods. For the rest of this talk, I would like to zoom in a bit more on this topic and discuss how different learning categories help realizing self-driving network dream. As you all know, there are 3 popular categories of machine learning algorithms in literature that we actively use in the context of self-driving networks. The first one is supervised learning. If one learns a task under supervision, someone is always present judging whether one is getting the right answer or not. Similarly, in supervised machine learning, there is a full set of labeled data as supervisors while training an algorithm. There are typically 2 areas in which supervised learning can help: classification and regression. The second method is unsupervised learning. Clean, perfectly labeled data sets aren't easy to come by, and sometimes we are asking the algorithm questions they don't know the answer to. That's where unsupervised learning comes in. In unsupervised learning, typically a deep learning model is handed a data set without explicit instructions on what to do with it. The training data set is a collection of examples without a specific desired output or correct answer. The deep learning engine, for instance, a neural network, then attempts to automatically find structure in the data and extracting useful features and analyzing its structure. So in effect, an unsupervised learning model solves a clustering problem, while supervised learning is about classification. The third category of learning algorithms is reinforcement learning. In this type of learning, the agents attempt to find the optimal way to accomplish a specific intent or to improve performance of a specific job. As the agent takes action, that goes towards the goal, it receives a reward. The overall aim is to predict the best next step to earn the biggest final reward. To make its choices, the agent usually relies both on learning from the past feedback and exploration of new tactics that may present a larger payoff. This involves a long-term strategy. We have already discussed that the primary function of a self-driving network is to take the intent, demystify it, convert it to a set of policies that need to be applied to different network and cloud components and execute them. Based on what we discussed, reinforcement learning is naturally a good fit for self-driving networks where we want to iteratively find the best way to go from current network states towards intended or desired states. Let's take a closer look on how reinforcement learning can help creating such functionality via an example. Suppose the intent is defined as to guarantee certain revenue by keeping the throughput of the network high, subject to no customer churn. The reinforcement learning engine, along with natural language processing techniques, has to map this intent to formal declarative policies, such as minimizing maximum link utilization of the network for a given demand matrix, subject to having protection against one link failure and a given upper bound for use capacity per link. Then in the definitive part, the system has to define policies for calculation of optimal paths and for each input demand to the network. Finally, the imperative policies could be those that are executing the optimal paths into the network by configuring the network elements accordingly. Along the way, computing policies such as scaling up policies to cope with the load if required will be added to the policy tree. Of course, in reverse order, a policy tree for monitoring and giving feedback needs to be designed and executed as well. Now let's look at how supervised learning plays a role in self-driving networks. Following same intent example that we discussed in previous slide, in order to make sure the best path is assigned to the demand, we need to label the input internet traffic as the dominant traffic of the network to delay sensitive and delay tolerant traffic at the edge. This helps the core engine in better decision making when there is resource contention in the network. Here is where supervised learning for classification helps. A sample mirror of the input traffic goes to a deep packet inspection engine that is responsible for determining application types within the mirror traffic. A table is already introduced identifying what application is delay sensitive and which one is delay tolerant. Based on that, the training data will be constructed and the supervised learning method, which is installed within the traffic classifier, will use it to label live traffic. The training data will be continuously refreshed to include possible new application types. The result of traffic classification will be given to another learning engine, which is a kind of decision tree algorithm. And in that, some policies will be identified to be installed in the router if required. For example, if the decision tree finds that all traffic coming from interface X are delay tolerant, a policy will be formed in the router to send all traffic coming from interface X to interface Y as the next step. Finally, let's look at one of the most difficult issues within telco service provider domains that self-driving networks are best positioned to deal with. Silent failures are those type of problems that are first reported by customer, meaning that our typical monitoring system have not been able to capture them. Up until recently, the silent failures were primarily caused by networking issues, or at least from network operators' point of view, they were network related. But nowadays, with the emergence of software-oriented modules as parts of network gear, the silent failures related to software are becoming more and more important. Given the nature of silent failures, we cannot use classification methods to categorize them since they need to be detected first. So the only option in front of us is to rely on proactive analysis or predictive analysis of any type of log that is generated in the network or within microservices and try to find anomalies primarily by detecting unusual correlations. So clearly, unsupervised learning methods are good candidates to help us in this situation. Given that we first need to detect anomalies and silent failures, clustering is the dominant method here. There are two types of clustering, partitioning and overlapping. In partitioning, each data belongs only to one category or cluster center, while in the overlapping method, the given data can be a member of more than one category. Combination of both partitioning and overlapping are required to tackle anomaly and silent failure detection and mitigation. Okay, let me stop here and conclude my talk by emphasizing on the fact that the concept of self-driving networks still is in its infancy, and there is a long but exciting journey ahead of us before we can claim self-driving networks are really existing, just similar to long journey of self-driving cars. Please feel free to reach out to me in case of any questions. My email is right here. Enjoy the rest of the conference, and wherever you are, please stay safe. Thank you very much.